what we're going to be talking about here in Chapter 9 is going to be about rational functions. And when we define a rational function, so when we talk about a rational function, basically what we're saying is that we just have a polynomial divided by another polynomial. That's basically what we're saying. Now we have to be a little bit careful about that so we don't rope in definitions of other things, because if you remember back when we defined what a polynomial was, that just a regular number also counted as a polynomial, right? Like 6 is also a polynomial. So we want to make sure that we're not including like constant functions or linear functions when we define these rational functions. So to do that, we're going to require that the numerator, the polynomial in our numerator, isn't the number 0, but any other polynomial is fine. And the denominator of our rational function, that's the q of x, has to actually have some x's in it, right? So it has to have degree at least 1. But that's it. The reason we don't want it to have degree less than 1 is because then we could have something like, x over 2, which is just 1/2 x, which is a linear function. And we don't want that, right? Because we've already talked about linear functions before. We need this to just be new stuff. So that's the idea. But the big takeaway here is just that it's a polynomial divided by another polynomial. Okay? Is everybody okay with that idea? All right. So thank you for responding. So just like we had talked about in first semester, we'll kind of be looking at our typical topics here. So I think when I outline this, I think it looks like we'll only really do 4 lectures for this topic. So we'll talk about simplifying. So today that means we'll talk about reducing, multiplying, and dividing rational functions. And then on Friday, we'll talk about addition and subtraction. And then after we come back from break, we'll talk about solving, but really that's a one-day topic. And then we'll talk about graphing, but really only one special case that I'll refer to as a simple rational function. And we should be able to do that in one day also. So really we have 4 lectures planned for this chapter. It should be considerably shorter than chapter 5 was. There's no big theorems. There's no, nothing like totally new technique-wise. It's going to be a lot of the same ideas that we've used before. And we're going to fall back into that kind of usual pattern of doing things. Is that everybody with an okay picture of what's going on? Now, certainly we'll take more than 4 class periods to do this chapter because we'll have some time in class to work on things and we'll do some review and all that kind of stuff. But basically, I have 4 lectures planned for this chapter. Is that okay with you guys? Just trying to give you a picture of kind of where we're going and what we're going to do. Paint you a little bit of a picture that 5 was as overwhelming at times as 5 felt. This should be considerably less so, as the topics, much fewer topics, much more familiar kinds of topics. There's no big theorems that we're going to use to like do something special for just this kind of for this kind of function. Okay, so let's move on and talk about these 3 topics for today: reducing, multiplying, and dividing. So here I'm going to use this term rational expression instead of rational function. So what would the difference between these be? Well, a function might be something like this. But an expression has no like y equals or f of x equals. It's just like the fraction. Everybody's okay with that? That it's basically still kind of the same thing. You can't graph an expression. You can't solve an expression. You can't do anything with that, like that with it, but it still looks very much like a function. You know what I mean? There's just not an input and an output space. There's just x's. Everybody's okay? So again, I didn't want to confuse anybody with that piece of vocabulary, that switch to calling something an expression versus a function. So I just felt like take a minute and clarify that. Anyways, that's kind of an aside. The idea here for reducing a rational expression, it's going to be just like reducing fractions. So let's just kind of go back in time, back to our, late elementary, early middle school, and try to remember how we reduced fractions. So let's take a super simple example like 2/4. How does that fraction reduce? Okay, turns into 1/2. How did you do that?
Yeah, so I don't know. I don't think about how I did it. It's just an 8. I don't know.
But like, what did you do to simplify?
Reduce. Well,
Okay, what, Alexis? What did you say? Divided what by what?
2.
Okay. So Alexis is saying we divided the numerator and denominator both by 2. And that gets to 1/2. Right? That's kind of what she's saying. That's probably what most of us did in our heads, or even if we couldn't articulate that. And that works reasonably well for fractions. What's going to be the problem with doing that if now instead of 2 and 4 having numbers, if we have a polynomial in its place?
Can't divide them. Is the exponent maybe?
Well, think back to chapter 5. Was it easy to look at a polynomial and tell what its divisors were going to be? No, right? We had to go and do a lot of guessing and a lot of theorem work to be able to do that, right? It was not trivial to find a divisor for a polynomial. So there's another equivalent way of thinking about reducing a fraction that I'm sure at some point you guys would have talked about in your elementary or middle school classes. So another way we can think about this is by factoring the numerator and denominator. So 2 is already prime, so there's no factoring there. But 4 factors into 2 times 2, right? And then we can reduce by canceling a 2 from the numerator and denominator. When we cross those out, those become 1s. And we're left with 1 on top and 1 times 2 on the bottom, or just 2. Do you guys kind of remember doing that before?
No. I know you did, but I know the top.
Okay. Okay. This is the preferred way of thinking about this, particularly when we start dealing with a rational expression, because oftentimes factoring a polynomial, we have a lot of shortcuts to do that, right? And a lot of time that's even really relatively easy to get the factoring done when it falls into like something that we could use the factoring tree with, right? We don't have to do the polynomial or the synthetic division stuff. We can just, if we can just use the factoring tree, that's pretty easy to do, as opposed to doing the polynomial division, which is always kind of a pain in the tuchus. So this is the kind of the way that we're going to think about things. So let's look at a couple of examples here. So let's say we have the rational expression x squared plus 7x plus 10 over x squared plus 9x plus 20. Note that these are both polynomials, right? You have a polynomial in the numerator, a polynomial in the denominator. Everybody agree with that? Okay. Let's see. Can I just do this? No. Why was I able to cross the 2's out in the example before, but I can't cross the x squareds out? Nope, that's not the reason.
Because it's like, one's in the, what's it called? Divisor, the numerator, like, it's at the bottom, and then on top. So it's like, can't do it.
I mean, we have the same situation, right?
Oh, it's true.
As far as one in the numerator, one in the denominator. There's something else, though, that's different. And it's not an exponent. That doesn't matter. What operation is going on between the things? So in the denominator, or in our rational expression example, we have addition going on between the terms, right? If we go back and we look at our fraction, what operation is going on? Multiplication. That's the difference. That is why it was okay to cross things off when we reduce the fraction, because the only operation going on is multiplication. Why it's not okay to cross off these x squareds is because the operation going on is addition. So for us to be able to reduce anything, we need to first change this problem from an addition problem into a multiplication problem. How do we do that? By factoring. So in all of our problems that we're going to do in this chapter, the first step is going to be factor. Because we cannot do any reducing until that is done. Whether we're adding or subtracting, multiplying, dividing, whatever, solving, the first step is always going to be to factor. So if we look at x squared plus 7x plus 10, that is a quadratic polynomial. Its leading coefficient is 1, so we should be able to do that with a shortcut, right? This is really a chapter 4 factoring problem. So what two things multiply to give me 10 and add to give me 7? 5 and 2. So that we can write as x plus 5, x plus 2. How does the denominator factor? 5 and 4. So I'll have x plus 5 and x plus 4. Now, if I look at this fraction, I have one thing multiplied to another thing. In the denominator, I have one thing multiplied to another thing. Everybody see that? Does it matter that there's addition and subtraction going on inside the parentheses? No, because the only operation going on outside of the parentheses is multiplication. Now we're in a place where we can reduce. So what parts are identical? The x plus 5s. Those can reduce, leaving me with x plus 2 over. No, because what operation is going on between the x's? Addition. Joe.
So then you basically reduce it into an expression, so since it's an expression, you can't do anything else to it?
Right.
So it's just like game over after that?
Game over. Yep. Since there's no equal sign, you can't solve or anything else. It just, you make it as simple as you can and then you move on.
Okay.
Let's do some more examples. Sound good? Okay. Here's our next example. In the numerator, we have 2x squared minus 4x. In the denominator, we have 6x squared minus 24. First step would be to factor. Okay, let's look at the numerator first. How can we factor 2x squared minus 4x? Well, it's not a difference of two squares. I heard somebody say that. And you know it's not a difference of two squares because we have an x squared in the first term and only an x in the second term, right? Yes. Oh, yes, sir. Go ahead. What else might we be able to do? Think back to your factoring tree. What's the very first thing we check for in the factoring tree? A what? A greatest common factor. Do you see a greatest common factor? 2x. Excellent. So after we factor the 2x off, what's left?
X minus 2.
Everybody agree with that?
Yeah.
Okay. How about the denominator?
6.
Okay, what's left after I take that off? Okay. Now, can I factor x minus 2 anymore? No, why not?
That's like middle.
It's linear, right? It's a degree 1. Can't do any more with a degree 1. Good. X squared minus 4. Can we do anything more of that?
Yeah.
Great. That is a difference of two squares, so it does factor to x minus 2, x plus 2. Can we do anything more with the x minus 2 or the x plus 2? No. So we factored this as far as it can go. Now it's time to look to reduce. The x minus 2's, okay. Anything else? There's a little more. So look between the 2, the x and the x minus 2, all multiplication, right? Between the 6, the x minus 2, the x plus 2, all multiplication. So the 2 and the 6, I can reduce like the fraction 2 over 6. Everybody's okay with that?
Yeah.
Okay, again, when we cross things out, they become 1s. We should get used to writing that down. So what am I left with in the numerator? 1 times x times 1, or just x. And the denominator, 3 times 1 times x plus 2. So 3 times x plus 2. There's no need to multiply anything back out. Just leave it in a factored form in the denominator is preferable. It's not that bad. Really, what's the hardest part?
Remember the rules to factor.
The factoring part, yeah. So again, it's a little bit new context or whatever, but not too bad. All right, let's do one more. Okay. So here, let's look at, in the numerator, we have 2x squared minus 4x plus 8. In the denominator, we have 4x cubed plus, oops, that should be, let's make that 32 is what I meant that to be. My apologies. I want to be able to do something with this problem. Okay. Let's look at the numerator first. What can we do to factor that?
The 2.
We can take out a 2. That's good. Let's look at the denominator now. What can we do to factor that? Yes, sir? Take out a 4.
We can do that even with a cube. Dumb question.
Greatest common factor is the greatest common factor. Doesn't matter the degrees. Everybody so far so good? So now let's go back and look at the x squared minus 2x plus 4. Can I factor that anymore? Are there two numbers that multiply to give us 4 and add to give us negative 2? What are they? Are there, so there's not, right? There's not. So that's as good as that one can go. Everybody's okay with that? The numbers that multiply to give us 4 are 1 and 4, 2 and 2, negative 1, negative 4, negative 2, negative 2. None of those are adding up to give us negative 2. Everybody's good? How about the x cubed plus 8? Can we do anything more with that? That's the sum of two cubes. Good. So again, the sum of two cubes factoring pattern is this. Hopefully at some point you're getting close to memorizing that, as it's come up quite a bit. So in this case, what is our value for A? Is x, and our value for B is 2. So when we plug those in then to our sum of two cubes factoring pattern, we have A minus B, A squared, I'm sorry, A plus B, A squared minus AB plus B squared. And if we recall, the the trinomial part of our difference of two cubes, never factorable. Or sum of cubes in this case, never factorable. The x cubed or x squared plus, or I'm sorry, minus 2x plus 4? Nope. So what multiplies to give you positive 4 and adds to give you negative 2?
No. No, I mean, like, can't you factor like the 2 and 4 out of it?
Okay, so you're talking about reducing.
Yes.
Yes. Now we're going to look for things to reduce. That's okay. I was just establishing that we were done factoring. You're already starting to reduce, which is fine, because we're done. We're talking about two different things. I'm confusing each other, I think. Okay, so Alexis is correct. We can reduce the 2. Is there anything else we can reduce?
That x squared minus x squared.
Yeah, that trinomial piece can also reduce. So what are we left with then in the numerator? 1. And in the denominator? 2 times x plus 2. What do you guys think? Not so bad, right? Now you see why I wanted to start this now, since the factoring was still pretty fresh for everybody. Imagine coming back to this 3 chapters later and having to remember how to do all the factoring again. Felt like it was just time to do this. Everybody good so far? All right, should we talk about multiplication? You guys ready to do that? So, multiplying rational expressions is going to be the same idea as multiplying. So let's go back here in time. Again, we'll get in our time machine, go back to late elementary or early middle school, and try to remember what this looked like. Do that, and then no, something like that. All right. Who remembers how to multiply 2 fractions? So cross multiplication is not a thing. Cross multiplication is a solving technique that you use to solve a proportion when you have one fraction equal to another. It is not.
Oh, you know, like add across, right? So you like 3 times across.
Multiply across.
Okay, so you can multiply straight across. Mhm. And then we would have to reduce. Okay. So what does this reduce down to? 7 over 6 maybe? What's the problem with this if we start thinking about, instead of numbers, having polynomials? So if we have multiplying 2 polynomials together, that was something we did last chapter. How'd you like that? It's kind of a pain, wasn't it? You have to do the superfoil or build the grid or whatever. So after we multiply 2 polynomials together, do the polynomials get more complicated or less complicated? More complicated. Is it easy then to reduce something that's more complicated? No, right? The factoring is going to get harder if you have to multiply the 2 together, right? So there's another way, another kind of order in which we can think about this problem that would make our lives a little bit easier. While what we did there was correct, what would be easier for us is if we reduced before we multiplied. So 10 is 2 times 5. 21 is 3 times 7. 77 is 7 times 11. And 20 is 2 times 2 times 5. That's equaling our polynomials to start with. And now we can reduce. And if we multiply across now, we're at the same spot, right?
How did you go from like, how did you drop it? Oh, wait. You did this.
I just reduced it. So things on the top reduced from things on the bottom. It didn't matter which fraction they're in.
Oh, you have to do that.
This will be much easier for us when we deal with rational expressions. And in general, this is even easier to deal with fractions because we never end up with a hard reducing problem like 770 over 420. We're only going to deal with little reducing problems, which are much, we'd rather do a lot of little ones than one big one, right? Typically is much easier. So let's do some examples. Okay. Okay. So here we have x squared minus 4x over x squared plus 5x plus 6 times x squared minus 9 over x squared minus 5x plus 6. We'll start by factoring. Everybody's okay? Okay. X squared minus 4, how does that factor? We did this already, didn't we? That was x minus 2x plus 2. Then x squared minus 9, how does that factor? Okay. And then x plus 2, x plus 3, good. That'll multiply to give us negative 6, though.
Oh, the other way.
That'll multiply to give you negative 6 still.
Oh, X.
Good. X minus 3 and x minus 2. Okay. Everything's all factored. Everybody agree? Mm-hmm. Where are your glasses?
Yeah.
Okay. Just saying. So let's reduce then. What can reduce?
The X has to, like, ground. Okay, wait, yeah.
Oops.
And X minus.
I thought I changed the color.
I think they're all.
So,
So it's
what?
1 over
Can you
1.
reduce it all?
they all can reduce. So this does end up just being 1 over 1 or 1. You are dead on. Now let's think about this problem. Was this any more difficult than the reducing problems? I mean, it was a bigger reducing problem, but it really just boils down to being a reducing problem, right? What do you guys think? Do we need to do another of these? You tell me. I already know how to do it. I'll do whatever you guys want to do. Just go.
It's not-
Megan?
Does that one like work out like easier or like is it like that?
I mean, it's just, they all boil down to being the same thing. You factor them, reduce everything you can. Whatever you can't reduce is your answer. You know what I mean?
I just can understand how you reduce the first one, like when you cross out the shift.
So like this 2 reduced with that 2. And then like this 5 reduced with that 5. That's all. Just like this x minus 2 reduced with that x minus 2. Right? You're welcome. So you'll notice, even to kind of really reiterate this, we started off with the multiplication of 2 fractions, right? When I wrote the factored form, notice I just wrote 1 fraction, right? Because it's really just one big reducing problem. You don't need to think about it as separate pieces. Just anything from the numerator can reduce with anything in the denominator. Donezo. Is that okay? Okay. Let's talk about division then. Guess what this is going to be just like? Yeah. Yes. Remember back in my elementary days, to divide fractions, my teacher taught us this rhyme. Dividing fractions is easy as pie. Flip the right and multiply was the rhyme that we learned, 30 years ago or whatever when I was in elementary school. So, for example, let's say we have 6 over 35 divided by 8 over 28. So this is just going to turn into 6 over 35 times 28 over 8. And then we proceed just like it would to be a multiplication problem. Exactly. So 6 is 2 times 3. 35 is 5 times 7. 28 is 2 times 2 times 7. And 8 is 2 times 2 times 2. So let's look at what we can reduce. That 2, that 2, that 2, that 7. And we're left with 3/5. Megan? Well, that's fine, but 4 is not prime, right? So you want to, when we're factoring them down, we want to factor them down to prime pieces. That'd be the same as like not completely factoring your polynomial, right? Like instead of taking out a 4, maybe you only took out a 2. You know what I mean? All right, let's do one more example here with rational expressions. All right. What should we do first?
Flip the right side.
Good. Let's turn this into a multiplication problem. Okay? So now it's a multiplication problem. What should we do next? X times what? Okay, which one are you factoring? Okay. So because the leading coefficient isn't 1, you're doing the long factoring, right? Because there's no greatest common factor, so you have to do that. Well, we're not trying to solve it, we're trying to factor it. So what multiplies to give us negative 120 and adds to give us 2? Should be relatively easy to find that. 12 and negative 10. So we can use that to set up our grouping. Right? Do we remember doing this from chapter 4? Okay, so from 8x squared plus 12x, we can take out a 4x. And from negative 10x minus 15, we can take out a negative 5. So that leaves us with 2x plus 3 times 4x minus 5. How about the x squared minus 9? X minus 3 and x plus 3. Okay. How about the x squared minus 7x minus 18? Okay. And then 4x squared minus 9? Good. Okay. And then what can reduce? Anything else? No. So that's going to just be our answer then. Notice that I am not going to multiply anything out. You could, it's not wrong to do that, but it's kind of like a gigantic waste of your time. So you do not need to multiply anything back out at the end. You can leave your answer in factored form. That's preferable, as it's much quicker for you guys, not have to do all that foiling, and it's much easier for me to grade if they're just in factored form. What do you guys think? Is division any harder than the other ones? You have that one additional step to turn into a multiplication problem, then it's just multiplication problem, right? What made this one longer or feel longer? We had to do that long factoring step in there. But that was a factoring issue. It had nothing to do with it being a division problem, right? Okay, this feels like a good place to stop.